In this lecture, we're going to look at the effect of external mass transfer on heterogeneous catalytic processes. At the end of the lecture, you will be able to understand external mass transfer effects on the catalytic process, define an external mass transfer limitation criterion, define the overall effectiveness factor, and develop homogeneous and heterogeneous models for packed bed catalytic reactors. In the previous lectures, we looked at the surface reaction steps: adsorption, surface reaction, and desorption, and the internal diffusion steps. That is, diffusion of reactants and products through the pores in the catalyst pellets. In this lecture, we will move out one more step to consider the external diffusion, which links the concentration at the catalyst surface to the concentration in the fluid bulk. We will also start putting this all together to formulate a model of a packed bed catalytic reactor. So instead of just looking at a single catalyst pellet, we will now consider the whole reactor. So how do we now consider the whole catalyst bed? We have defined negative RA as the reaction rate per volume of catalyst. We started with negative RA prime, which was per kilogram of catalyst, and we multiplied it by the catalyst density to get it per unit volume of catalyst. Now we want to work out how big the reactor needs to be, and for that we want the volume of the catalytic bed rather than the volume of the catalyst itself. To do this, we need to define two new quantities. The first is the bed void fraction, epsilon b. This is the volume of the bed not occupied by catalyst particles. We can then use this to get the bed density, which is the mass of the bed divided by the volume of the bed. So it will be smaller than the catalyst density because the bed volume includes all of the void spaces. The bed density is the catalyst density multiplied by the fraction of bed volume that is catalyst pellets, or 1 minus epsilon b. Using these definitions, we can now define the rate of reaction per volume of bed, which is negative RA prime times the bed density, and that is equal to negative RA prime times the catalyst density times 1 minus the bed voidage. Looking at the external diffusion now, just as we had different criteria to describe the relative rates of surface reaction and internal diffusion, the Tila modulus and the Weiss-Prater criterion, we also have a criterion to help us determine when external mass transfer is relevant. One measure is called the Mears criterion, which uses the observed or measured rate of reaction, catalyst size, mass transfer coefficient, and bulk concentration to determine if mass transfer from the bulk phase to the catalyst external surface can be neglected. In the numerator, you can see the rate of reaction per unit volume of bed that we defined in the last slide. This is multiplied by the catalyst pellet radius and the reaction order. In the denominator is the mass transfer coefficient and the bulk concentration. This is the maximum rate of external mass transfer you can expect when CAS is equal to 0. Remember that the mass transfer flux is the mass transfer coefficient, Kc, times the difference between the bulk concentration, CAB, and surface concentration, CAS. If external mass transfer is negligible, we can assume that the bulk concentration, CAB, is equal to the surface concentration, CAS. By external mass transfer, we mean the transport of reactants from the bulk fluid phase to the surface of the catalyst pellet. Also the transport of products from the surface into the bulk. You should remember this from your previous modules on mass transport. To work out the rate of mass transport from the bulk to the catalyst surface, or the other way around, we usually use stagnant film theory, which says that there is a stagnant film around the surface of the catalyst and that all resistance to mass transport is in the film. The rate of mass transfer is proportional to the difference in concentrations in the bulk and at the catalyst surface, and the constant of proportionality is the diffusivity divided by the thickness of the film. We can think of the thickness of the film as the resistance to mass transfer. Generally, we call the diffusivity divided by the film thickness as the mass transfer coefficient, denoted by K and a subscript depending on where the mass transfer is taking place. So for a liquid, the mass flux from the bulk to the surface of the pellet is CAB minus CAS times the diffusivity of A in the liquid divided by the film thickness. And this is equal to the same concentration difference times by the liquid mass transfer coefficient, KL. So for liquids, we have KL equal to DABL, so the diffusivity of A in the liquid, divided by the thickness of the film, delta L. For gases, it's just the same thing, but with the gas diffusivity and gas concentrations. However, we can also express the driving force in terms of partial pressures. Assuming ideal gas, we can write the flux as the difference between the partial pressure in the bulk phase minus the partial pressure at the surface of the catalyst times the gas diffusivity of A divided by RT times delta G, the gas film thickness. You divide by RT just like we did in topic 2 for the Langmuir isotherms and Langmuir-Hinshelwood expressions. Then the DABG divided by RT delta G is called the gas mass transfer coefficient, Kg. So for gases, we have Kg equal to DABG divided by RT delta G. In this lecture, because we are only considering two phases, solid in liquid or solid in gas, we don't have to distinguish between the mass transfer coefficient for liquid and gas. So we just use Kc as a general symbol for mass transfer coefficient. So if we know the mass transfer coefficient Kc, we can relate the bulk and surface concentrations of the species in our system. That means we can calculate the rates of reaction in terms of the bulk concentrations. which are things we can measure. And that's what we need to do to design our reactors. We always have to use bulk concentrations. So how do we get the values of the mass transfer coefficient, Kc? We can do specific experiments to get them, but if we are designing a reactor, that may not be possible. In that case, we can use correlations. One such correlation is by Frusling, which is shown here for two different shapes of pellet. This correlation relates the Sherwood number, which contains the mass transfer coefficient, Kc, to the Reynolds and Schmidt numbers. All of the parameters in this equation are things that we can control or physical properties of the fluids. So we can decide what the catalyst pellet diameter is, and we can choose what the fluid velocity will be by designing our reactor in a particular way. The other parameters are diffusivity, density, and viscosity, all properties of the fluid that we can look up. So that means that we can calculate the mass transfer coefficient, Kc. Ultimately, what we want to do is calculate the rate of the reaction considering external diffusion, internal diffusion, and reaction. To do that, we need to understand the rate of mass transfer from the bulk phase to the surface of the catalyst. Once we know that, we can relate it to all the other rates we have calculated for the pellet, internal diffusion and reaction. We know that the molar flow rate of mass transfer, Ma, is the molar flux in the radial direction, WAR, multiplied by the area through which the material is flowing. For catalyst pellets, we define AC as the external surface area per unit of reactor volume. So we have Ma is equal to WAR times AC times V. V is the volume of the reactor. At steady state, the molar rate of transport of A to the surface of the catalyst pellet must be equal to the total rate of reaction on the surface of the catalyst pellet as well as inside it. So the external area is, as we have just seen, AC times V, which is the area per unit volume times the reactor volume. We can calculate the internal area as follows. First, take the internal area per unit mass of catalyst SA. Then multiply that by the catalyst density, rho C. That gives us the surface area inside the catalyst per unit volume of catalyst. However, we want it per unit volume of reactor. To get that, we multiply by 1 minus epsilon B. Epsilon B is the void fraction of the packed bed. That is the volume of free space between the catalyst pellets divided by the total volume. So 1 minus this is the volume of catalyst pellets divided by the total volume. Now we have the surface area per unit total volume. We just multiply by the reactor volume to get the total internal surface area. Now we can put this into our expression for the rate of reaction in and on the surface of the pellet. So we have Ma is equal to negative Ra double prime times the external surface area plus the internal surface area, which becomes negative Ra double prime times the sum of AC times V. So this is the external surface area, and SA times rho B times V. so the internal surface area. Remember that the bed density, rho B, is the catalyst density, rho C, times 1 minus epsilon B. Finally, putting these two expressions together, that the mass transport of A into the surface of the pellet is equal to the total rate of reaction, gives us that WAR times AC is equal to negative RA double prime times the sum of AC plus SA times rho B. Remembering that this is true at steady state only. Now, looking at the two surface areas, the internal surface area is much larger than the external surface area for most catalysts. Therefore, we can neglect the external area because it is insignificant compared with the internal area. This simplifies our equation that relates the external mass flux, WAR, to the internal reaction rate. We need to get an expression for negative RA double prime. Remember that this depends on the radial position in the catalyst pellet, but we can introduce this dependence through the effectiveness factor. In topic 3, we saw that the overall rate throughout the pellet is related to the rate at the surface conditions through the effectiveness factor. So negative RA double prime is equal to negative eta, so our effectiveness factor, times RAS double prime. So this is the rate at the surface of the catalyst. So our equation becomes WAR times AC is equal to negative RAS double prime, so rate at the surface of the pellet, times eta, the effectiveness factor, times SA, the specific surface area, times the density of the bed, rho B. We also know what WAR is, since this is the flux of A arriving at the surface of the pellet from the bulk phase. This is equal to the mass transfer coefficient, Kc, multiplied by the concentration difference, CAB minus CAS. Therefore, Kc times CAB minus CAS times AC is equal to negative RAS double prime times eta times SA times rho B. Finally, if we assume a first-order reaction, we can relate RAS double prime to CAS. And this will help us relate CAS, so the surface concentration, to CAB, the bulk concentration, which is what we ultimately need to design the reactor. So for a first-order reaction, negative RAS double prime is equal to K1 times CAS. And substituting that into our balance between the mass transferred flux and the reaction inside the pellet gives us the following expression. So Kc AC times CAB minus CAS, and this is equal to the effectiveness factor eta times K1 times SA times rho B times CAS. We can rearrange this to get CAS in terms of CAB and the other parameters, which we can substitute into the expression for negative RA double prime. Now we have an expression for the overall rate. So the negative RA double prime that depends only on quantities that are measurable or calculable. Before, when it depended on CAS, it was not so convenient. We can rearrange the expression for the rate of the reaction, negative RA double prime, so that it looks like negative Ra double prime equal to a constant times K1 times the bulk concentration, CAB. This looks like how we related the rate of reaction to the surface concentration, CAS. So we had negative Ra double prime equal to the effectiveness factor eta times K1 times CAS in topic 3, where we ignored the effect of external diffusion. But now in this lecture, it is in terms of CAB, the bulk concentration. This constant is called the overall effectiveness factor with the symbol of capital omega, and it takes into account the resistances due to external diffusion, internal diffusion, and reaction. You can see this is because it is a function of both eta, the effectiveness factor, in the last topic, topic 3, which accounts for the resistances due to internal diffusion and reaction. And we have KCAC here, which accounts for the resistance due to external diffusion. Note we have two effectiveness factors. If we simply say effectiveness factor, we mean the internal effectiveness factor, denoted by eta, which accounts for the resistances due to internal diffusion and reaction. We also have the overall effectiveness factor, denoted by capital omega, which accounts for the resistances due to external diffusion, internal diffusion, and reaction. So we write the rate of the reaction, negative Ra double prime, is equal to omega times K1 times the bulk concentration, CAB. If we rearrange this, we get omega equal to the rate of the reaction, so negative Ra double prime, divided by K1 times CAB, or the actual observed overall rate divided by the rate if the entire surface of the catalyst were exposed to the bulk concentration, CAB. That is, if there were neither internal nor external resistances. So the overall rate is negative Ra double prime equal to omega times negative Rab double prime, which is the rate at the bulk concentration. And this is equal to omega times K1 times CAB for a first order reaction. And recall the relationship between the different rate units. Negative Ra double prime is per square meters of catalyst surface. Okay, so per unit area of catalyst surface. And negative Ra prime is per kilogram of catalyst. And negative Ra is per cubic meter of bed or reactor. So negative Ra prime is SA times negative Ra double prime. Then negative Ra, which is per cubic meter of bed, is rho B, so the catalyst bed density. So that's the units is kilogram catalyst per cubic meter of bed times negative Ra prime. This is per kilogram catalyst. A dimensionless number, the BU number, has been defined to describe the relative importance between internal and external resistance in catalytic processes. It is defined as the BU number, so Bi, it is equal to the mass transfer coefficient Kc times the catalyst particle diameter dP divided by the effective diffusivity dE. Remembering that Kc is equal to dAb, the diffusivity of A in B, divided by the delta, the film thickness, we can write the BU number as dP over dE divided by delta over dAb, which is the ratio of the internal diffusion resistance to the external diffusion resistance. Thus, if the BU number is low, that is, if it's less than 1, then the external resistance is greater therefore more important than internal resistance, though there can still be some internal resistance. Similarly, if the BU number is greater than 1, then the internal resistance is more important. Now that we have a way of relating the overall reaction rate to the bulk fluid concentration, we are ready to develop models of whole reactors so that we can design them and analyze their performance. We will start with a homogeneous model of a packed bed catalytic reactor, accounting for the external mass transfer limitation, as well as, of course, internal resistance in the pellets. In a homogeneous model, you consider all phases together as one, so gas plus solid together, or liquid plus solid together. Since we don't account explicitly for the solid as a separate phase, we use the overall effectiveness factor, omega, to account for its effect on the overall reaction rate. So our system is as follows. We have a cylindrical vessel of cross-sectional area, AC, and length L, filled with a bed of catalyst. This will be a one-dimensional model, so there is one coordinate, Z, in the axial direction of the reactor. Our control volume will be a differential element at Z with length delta Z and volume delta V. We define the volumetric flow rate of fluid. So volumetric flow rate, the unit is cubic meter per second as small v, and the superficial velocity as capital U. So if you can remember, the superficial velocity is the velocity of the fluid if there were no packed bed in the vessel. In other words, the vessel is empty. So it is equal to the volumetric flow rate divided by the cross-sectional area, AC. The actual velocity will be higher because there is less area for the fluid to flow in when there is catalyst in the bed. But it's more convenient to use superficial velocity. To develop the model, we write a material balance for A over the differential element at Z. The rate of flow in of A is WAZ, so the molar flux in the Z direction. So at Z times the cross-sectional area, AC. The rate of flow out is WAZ at Z plus delta Z, again times the cross-sectional area, AC. The generation term is the rate of formation of A, which is RA prime. So note that we are using the per kilogram basis for the rate because we want to multiply it with the density of the bed and then times the volume of the differential element. So it is convenient to express the rate in terms of per kilogram catalyst. Okay, so rate of formation of A, this is RA prime times rho B. So rho B is a kilogram catalyst per cubic meter of bed times the volume of the differential element. So the volume of the differential element is just the cross-sectional area, AC, times the length of the differential element, which is delta Z. In minus out plus generation is equal to accumulation. We will develop a steady state model in this lecture, so the accumulation term is 0. Now we divide by AC delta Z and take the limit as delta Z goes to 0 to give us the following differential equation. The molar flux of A has two components: diffusion, given by Fick's law, and convection. Convection is the transport of matter due to the bulk motion of the fluid. So we can define WAZ. So this is the molar flux of A. In the Z direction, this is equal to minus DAB. So this is the diffusivity of A in B times the change in concentration in the bulk phase with respect to Z. Okay, so this is just given by Fick's law plus the term due to convection. So we have the superficial velocity times the bulk concentration. Okay, so the flux due to convection is just the velocity times the bulk concentration. So substituting this into our differential equation gives us the following second order differential equation. There is a term for diffusion or axial dispersion, a term for convection, and a reaction term. Axial dispersion is used when you have backmixing due to turbulence or a radial velocity distribution. You can replace the diffusivity AB with dA, which is the axial dispersion coefficient. Do you still remember the difference between diffusion, dispersion, and convection? So diffusion is due to the motion of the individual molecules in the fluid. It is typically slow. Dispersion is the relative motion of different fluid elements due to turbulence or due to velocity gradients. You may remember the term eddy diffusivity in relation to turbulence. It is the rate at which small elements of the fluid, which move in a random way because of the turbulence, mix with each other. When you have a velocity gradient, the fluid at the center of the reactor is moving faster than the fluid near the wall. So there is dispersion due to that. Finally, convection is the motion of the bulk fluid. So diffusion is at the molecular level, convection is at the bulk level, and dispersion is in between but closer to bulk motion. Finally, we just need to include the reaction rate. In the previous slides, we derived the overall effectiveness factor omega, which accounts for external and internal resistances. We established this relationship that negative RA prime is equal to negative RAB prime. So now it is at the bulk concentration. Okay, so times omega, which is the overall effectiveness factor. Okay, or the actual reaction rate is the overall effectiveness factor multiplied by the rate at the bulk concentration. For a first order reaction, we have negative RAB double prime is equal to K1 CAB. So if you write the rate this way, the unit is per surface area of the catalyst. Okay, so per square meters of catalyst surface. Okay, but here we want per kilogram of catalyst. Okay, so we have negative RA prime. So we need negative RA prime AB. So we just need to multiply the negative RAB double prime with SA. Okay, so therefore, negative RAB prime is equal to SA times K1 times CAB. So therefore, negative RA prime is equal to omega times the rate at the bulk concentration, which is SA K1 times CAB. Substituting this into our differential equation, so the expression for RA prime into here, gives us our final model equation. This is the only equation we need for the model because it is a homogeneous model, meaning there's only one balance and one concentration. All of the particle effects, external and internal resistance, are lumped into the reaction term using the overall effectiveness factor, omega. This equation is difficult to solve analytically, so typically you would use something like MATLAB to solve it numerically. It can, however, be solved analytically if you make some approximations. One approximation that can be applied is to neglect the axial dispersion term. This can be done if the superficial velocity is large enough. The test for this is that the rate of reaction divided by convection should be much smaller than the particle Peclet number. So that's convection over dispersion. If this is the case, then we can assume the convection term is much larger than the dispersion term, and it is safe to neglect the dispersion term. This then simplifies our model equation to the following first-order differential equation, which we can easily solve analytically. You can just integrate it using the limits. CAB is equal to CAB0, so the inlet concentration of A in the bulk phase. And at Z is equal to L, CAB is equal to CAB. So this gives you the simple exponential relationship between outlet concentration and reactor length. And we can also write this in terms of conversion. So the conversion at the exit of the reactor is equal to 1 minus the exponential of this whole term here, which has the overall effectiveness factor, omega. So using this equation, you can determine the length of the reactor required to achieve a certain conversion. Now we will look at a heterogeneous model for a packed bed reactor. In a heterogeneous model, the gas and solid phases are considered separately. So here we are considering gas and solid phases, but it is also possible that you have a liquid and solid phases. So in this example, there will be no reaction in the gas phase. So there is mass transfer between the gas and the solid phases, and the reaction takes place only in the solid phase. We will assume steady state in both phases, and we will derive separate material balances and energy balances for each phase. Just as we did for the homogeneous model, we start with a standard material balance, where the accumulation term is 0 since we assume steady state. The rate of mass transport of A from the gas to solid phase is the usual expression involving the mass transfer coefficients and surface area of pellets per unit volume of bed. Dividing by AC delta Z and taking the limit as delta Z goes to 0 gives us a differential equation involving the molar flux WAZ. The flux is given as usual by the diffusion or dispersion term plus the convection term. Substituting this into the differential equation gives us the model equation for the gas phase. For the material balance of A in the solid phase, there is no flow of A in the axial direction. There is only transport of A from the bulk gas phase to the solid surface. So we write the rate of transport of A to solid phase plus the rate of generation of A equal to 0. 0 because we assumed steady state. So we are saying that the rate of transport of A to the solid phase from the gas phase is equal to the rate of consumption of A. We can write the rate of generation of A, so that's negative Ra prime, as the effectiveness factor multiplied by the rate at the surface concentration of A, thus accounting for the internal mass transport resistance in the pellets. For a first-order reaction, this becomes eta, the effectiveness factor, times SA times K1 times CAS. Substituting into our material balance and dividing by AC delta Z gives our final equation for the solid phase. The material balance for A in the solid phase can be used to obtain an expression for the surface concentration of A, CAS. So we can rearrange this and solve for CAS, similar to what we did to calculate the overall effectiveness factor. And then we substitute this expression for CAS into the right-hand side of the material balance for A in the solid phase. So here. And then use this term, so KCAC times CAB minus CAS, to eliminate the KCAC term in the gas phase material balance. Okay, so substitute this term here into this term. Okay, so doing that will give us this expression. And then we assume that dispersion or diffusion is negligible. So we can drop the second derivative term, and remembering the definition of the overall effectiveness factor, we can substitute this in and see that the equation is the same as the homogeneous model. It may not always be possible to combine the equations for the gas phase and the solid phase in this way. For example, if it's not at steady state. In that case, the two equations have to be solved simultaneously. Finally, we have an energy balance for each phase. This is the energy balance for the gas phase, and this is the energy balance for the solid phase. I have uploaded the derivation of these equations onto Moodle, so look for the download link below this video in Moodle. These equations are coupled with the material balance because we need the rate of reaction from the material balances to know how much heat is released. Ts, which is needed in the gas phase balance, is determined from the solid phase equation. Generally, the rate of catalytic reaction also depends on Ts through the temperature dependence of the rate constant K1. So you cannot combine these equations. So you have to solve them simultaneously, also with the material balances. You can use a numerical method and implement the solution in MATLAB using what you learned from your Advanced Process Modeling module. In the exam, you will not be expected to derive the energy balances for packed bed catalytic reactors. To summarize, in this lecture, we looked at the effects of external mass transfer on the overall reaction rate of catalytic processes. This can be represented by the overall effectiveness factor omega, which is the actual observed rate divided by the rate that you would get if the entire catalyst surface were exposed to the reactant at the bulk concentration CAB. We derived an expression for the overall effectiveness factor in terms of the effectiveness factor, eta, the intrinsic rate constant, K1, the specific surface area of catalyst, SA, the bed density, rho B, and the external mass transfer properties, Kc and Ac. We also looked at the Mears criterion, which can be used to determine whether or not external mass transfer resistance can be neglected. The BU number also gives you some idea about whether or not external mass transfer can be neglected. It is the ratio of internal diffusion resistance to external diffusion resistance. So a large BU number means that the internal diffusion resistance is much more important than the external resistance. We then derived a homogeneous model of a packed bed catalytic reactor. If we can neglect axial dispersion and diffusion, then we were able to solve it analytically to give the following solution. So the bulk concentration of A, CAB, is an exponentially decaying function of the position in the bed. This can also be rearranged to give the outlet conversion of A. So this is our design equation. So for a given length of the reactor, we can determine the conversion and the other way around. So for a given conversion, using this equation, we can calculate the length of the reactor that is required. Finally, we derived a heterogeneous model for a fixed bed catalytic reactor. This resulted in the following two equations for the bulk and surface concentrations. So the two equations need to be solved simultaneously